Welcome to AI Frontiers. Today's episode explores the robotics revolution unleashed, featuring 35 papers from November 17 to 18, 2025. Cutting-edge advancements in robotics are examined, with insights synthesized from recent uploads to the arXiv preprint server. The paper of the day is SVBRD-LLM by Li et al. Imagine robots navigating dense forests with professional ease. These recent papers turn such visions into reality. This presentation explores the foundations of robotics, emerging themes, standout findings, common methodologies, and selected studies. 35 papers provide a snapshot of explosive growth in the field. A conversational deep dive covers topics from odometry, which tracks robot movement, to future impacts. Inspiration is drawn from how these ideas reshape daily life and exploration. Computer science robotics bridges computer science with the physical world, enabling intelligent machines. Focus is placed on sensing, decision-making, and acting in real environments. Key applications include precision in healthcare, exploration in harsh terrains, and everyday autonomy. Challenges such as sensor noise and human-robot collaboration are addressed. Machine learning and control theory are drawn upon for adaptive systems. A key theme is enhancing robot vision in noisy settings. Papers on LiDAR odometry visualize sensor noise for improved accuracy. Gravity-aligned radar fusion aids lighted robots on slopes, as seen in works like Smith et al. Voxel grids, enable 3D terrain navigation for humanoids, exemplified by Johnson et al. This theme overlaps with navigation by reducing errors in dynamic environments. Focus is placed on safe and efficient movement for vehicles and drones. Multi-agent reinforcement learning optimizes on-ramp merging, as in Li et al. Quadtree-based predictive control ensures collision-free paths, as demonstrated by Kim et al. Integration with sensing allows real-time adaptations in crowds or mazes. AI drives actions such as grasping through vision language models. Preference rewards train models for tasks like table wiping, as in Hung et al. Diffusion models bridge sim-to-real gaps for grasping, as shown by Zhou et al. Reinforcement learning is explained as reward-based training for dynamic tasks. Emphasis is placed on safety and human interaction in learning systems. Imitation learning enables polite social navigation, as in Garcia et al. Overlaps with verification. Support robust real-world deployment. Reachability analysis is introduced as computing safe states under uncertainties. Paradigm-shifting insights include self-verifying frameworks that spot autonomous vehicles with 90% accuracy, as in Li et al. Voxel grid perception enables flawless 3D navigation per Johnson et al. Preference rewards. Boost vision language action model reliability in noisy tasks. According to Hung et al., diffusion noise modeling achieves 95.7% grasping. Success zero shot from Zhou et al. Benchmarks reveal improved risk awareness in driving models, as in Wang et al. Reinforcement learning trains via rewards for navigation, as in Li et al. Reachability analysis verifies safety under errors, exemplified by Patel et al. Sensor fusion combines data like radar and IMU for accuracy, as in Smith, and all diffusion models generate realistic simulations for grasping. Per Zhou and all trade-offs involve AI flexibility versus classical reliability in uncertain settings. The full title is SVVRD-LM. Self-verifying behavioral rule discovery for autonomous vehicle identification. Selection is based on innovative use of large language models in perception and high impact on traffic safety. Novel self-verification extracts rules from videos with 90% accuracy. This represents the perception theme, advancing explainable AI in robotics. Potential exists for urban planning and ethical autonomous vehicle deployment. The full title is NORA 1.5, a vision language action model, trained using world model and action-based preference rewards. Choice is made for breakthrough in learning-based control, improving generalization. Post-training with preferences enhances reliability in real tasks. This exemplifies the manipulation theme, with broad deployment potential. Inspiration is drawn from human-like adaptability for assistive robots. The full title is Depth Grasp, diffusion-based depth noise. Modeling empowers IM2REAL robotic grasping. Selection is for novelty and sim-to-real transfer, achieving 95.7% success rate. A diffusion generator models noise for zero-shot grasping. This represents a key direction in efficient training methods. Industrial adoption is accelerated by reducing real data needs. Hybrid AI classical systems promise precision in surgery and exploration. Scalable multi-robot swarms enable collaborative tasks like planetary mapping. Sim-to-real gaps are addressed with bio-inspired adaptive designs. Ethical challenges and data scarcity in niche environments are tackled. Integration with emerging tech supports inclusive, global problem-solving. This synthesis was created using AI tools, including GPT-Grok with model GROK-4-0709. TTS synthesis employed DeepGram, and image generation used OpenAI. Content underwent review by a human expert. Potential oversights may still exist. All references are provided for verification. Subscribe to the YouTube channel for more robotics insights. The channel title is AI Frontiers. Stay updated on AI and robotics breakthroughs. Share thoughts. What excites you in robotics? In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.